Atsegina da oso niretzat Roald Hoffman profesorea aurkeztea. Gaur arratseko islaria eta inoiz aurkitu izan dudan islarerik onenetarikoa dena. Argia benetan esanak esateko eta esan ohi dituenak argiak oso izaten dira. Roald Hoffman 73 urte duela jaio zen. Gaur egun Ukrainia den, baina bera jaio zenean Polonia zen herrixka batean. Bigarren mundu gerratik bizirik atera, etzen gutxi izan hori, eta Estatu Batuetara, New Yorkera injustu, etorkin askoren antzera iritsi egin zen. Roald unibertsitate ikasketak burutu zituen Columbia eta Harvard unibertsitateetan. Eta gaur egun Cornell unibertsitatean egiten du lan. Roald Hoffmanek jaso egin ditu jadanik imagina itezkeen zientzia sari gehienak. Hoien artean, nola ez aipatu, 1981 urtean jaso zuen Nobel kimika saria. Erreaktibitate kimikoari buruz egin zituen aurkikuntzen garrantzia aitortzen duena. Izan ere, Robert Woodwardrekin batera ebatzi egin zuen erreakzio periziklikoen estereokimika orbital molekularren simetriari zeriela. Gaur egun Woodward Hoffman simetria arauak bezala ezagutzen ditugu eta jadanik testu liburu materiala dira. Hemen zaudeten ikasle guztiak oso ongi dakizuten bezala, ziur naiz hontaz. Hau guztia nahikoa izango ezpalitz, Roaldek sistema infinitoen kimika eta haien gainazaletan gertatzen den kimika ipini izan ditu oinarri sendoen gainean. Fenomeno katalitikoen ezagutzan hainbat ekarpen garrantzitsu egin bai ditu, besteak beste. Azken aldi honetan, Roaldek imaginazioa jarri du lanean berak dioen bezala leku oso estuetan. Edo beste modu batera esan da, presio handiko baldintzapetan gertatzen den kimikan. Zalantzarik ez, gaur azken urte hauetako luminari bat dugu islari. Utzi egidazue luminari hitzaren esan nahia Oxford Advanced Dictionary of Current English etik jasotzen. Honela dio, luminary, number 1, person who because of his learning is like a shining light. Number 2, great moral or intellectual leader. Roaldek ezaugarri hauek biak betetzen ditu. Argi dirdiratsua da zientzian, haren lidergoa uka ezina delako. Eta bestalde, bere handitasun morala eta zientzilariek gai sozialetan duten ardurari musin egin ez diezaioten ohartzeko egin duen lana ere aipagarriak dira. Roald Hail, an international journal for the philosophy of chemistry, aldizkariaren zientzia batzordekidea da. Era berean, harrigarria da, zein modu naturalean iritsi zaion Roalden mezua publiko arruntari, ez espezializatuari. Idazle bezala duen kurrikuluna ere ez da nola nahikoa. Zientzia, poesia, antzerkia eta filosofia eremuak eta tarteko landak goldatu egin ditu hainbat saiakeratan eta nidakianez 3 liburutan. Poesiari ere egin dio kasu egin ere, eta 2 poesia bilduma argitaratu ditu. Gainera Roald antzerki idazlea da. Lagun eta lankide duen Carl Gerasi, Stanford Unibertsitateko kimika profesorearekin batera Oxygen izeneko antzerki lan argitaratu dute. Aparte, beste 2 antzerki lan idatzi ditu Roald Hoffmanek. Azkenik, eta propaganda handirik gabe, Roald zientzia ikuskizu baten arduraduna da, Cornelia Street Cafeen antzesten dena, New Yorkeko Greenwich Village auzoan. Baina lehenengo eta behin Roald, esan dezadan, Roald irakaslea da. Guztiz doaitxua eta sekulako intuzioa eta pasioa duena, bai ikerketarako, baita egiten duen zientzia publikoari komunikatzeko ere. Hau guztia esan da, hobe dut behingoz isiltzea eta hitza eman diezaiodan gure gaurko islariari. Roald, please, you have the floor.
Yes. I'm going to give you 3 views of chemistry. And the first of these is an old one, that chemistry is the art, craft, and business. It always was a business. You need an economic basis for anything we do, of substances and their transformations. And this definition of chemistry preceded the existence of chemists as scientists, and even the word chemistry, because people were put on this earth to transform it, and they change it in essential ways. Let me give you an example. At the top are 3 works of art of our civilization. At the left, a wall painting from Luxor in Thebes. At the center, a gate of Ishtar, which once stood in Babylon, and then through a feat of imperialism for a change not American, found its way to Berlin. And at right, you see an example of Hellenistic painting, a form of realistic representation with all the limitations on what realism means, which preceded the Italian Renaissance by 1,500 years. The green and the blue in these is not a natural pigment. There was a blue that was available. It was, as is today, expensive. It was lapis lazuli, ultramarine, and you can see it in the paintings of the painters who had access to it in the Renaissance. But the blue and the green here from the blue are both something called Egyptian blue, which is shown as a powder at the bottom here. It is a product of human transformation coming out of the preeminence of the Egyptians in making glass and enamel, and it's essentially a powdered glass of a blue pigment which contains the same components as glass, that is sodium carbonate, natron, and silicon dioxide, but also has a little bit of a copper mineral that is used as the source of the color. The structure is shown at right, but it's not really important. The important thing is this was an article of commerce in the ancient world, made by human beings, exported and sold, made reproducibly, and it was chemistry, before there was chemistry. Now, I want to really show you chemistry. What I need to do is a demonstration. And I did not know if the safety committee of the Kursal would allow me to do a demonstration here. And so I brought some slides. Here are 2 substances. At left you see bromine, a reddish-brown liquid and gas above it. At right you see aluminum. These substances were actually not available to human beings until just about 200 years ago. But then they were available. Aluminum, for instance, 200, 150 years ago even, was so expensive that Napoleon III served his most eminent guests on a dinner service made of aluminum, and his second most important guests on gold. The tip of the Washington Monument, when it was constructed, was made of aluminum. And it was only 5 years after that monument in Washington was constructed that a young man, 23 years old, in Ohio, and another young man in France found a way to make aluminum as cheap as it is today. We want to see what happens when you have, these are the substances. One is placed into the other, and you see flames, smoke, foul odors, absolutely everything you expected of chemistry, isn't it? And at the end of that is something else, something fundamentally different, nothing like the two previous substances it came from. It happens to be a complicated aluminum bromide. This is chemistry. This was always chemistry. If foul odors, explosions, and colors are what attracted young people to chemistry and always will attract young people to chemistry. If you want to read a good introduction to this that is outside of my own field, you can read the memoir by the neurologist Oliver Sacks called Uncle Tungsten about his chemical boyhood. Now, it does not have to be happening like that. Chemistry happens everywhere. Here is a place where chemistry happens, which is absolutely special to Basque cuisine. And it happens both in the animals that are grown in here and in the cooking process of these animals. But I wanted to show you the previous slides. Chemistry is happening in this as well. There are some consequences of this definition of chemistry, that it's things and their changes, and that sometimes the changes are dramatic, as you saw in that aluminum and bromine example. And this is exemplified by this. So this is a 1942 Donald Duck comic book. In those days, the entire comic book, the story and the pictures were drawn by one person, Carl Barks, one of the initial collaborators of Walt Disney. Here is the first set of panels. Some of you can see it, but as you know from Donald Duck comic books, you don't have to know exactly what is said there. What happens is the nephews are doing something, Donald Duck comes in, he does something stupid, no one is wearing safety glasses here. There is an explosion. There is the inevitable egg upon the head that happens in every Donald Duck comic strip. What's interesting about this, at the bottom right, my colleagues are complaining there is not enough chemistry before the general public. But there are some chemical formulas. Actually, the most interesting thing is this next panel, which I've enlarged, where Donald Duck says, if I mix CH2 with NH4 and boil the atoms in osmotic fog, I should get speckled nitrogen. And the nephews comment appropriately. Why is this interesting? Because this reaction has not yet been done. And you have to be a chemist or have a friend as a chemist to tell you why it's difficult to do this particular reaction that is here. Why do I show this to you? Of course, because it's fun. But in part, I show it to you, and I will come back to this, because it is inevitable that people will think of chemists as a result of chemists having to do with fundamental transformations. It is inevitable that people will think of chemists, that chemists are the people who make things go bang. And it's something we have to live with. And I'll come back to that in a while. Now, I want to tell you about that is, in a sense, what you saw in a comic book is one interaction of chemistry with society. A comic book represents that. Here is another interaction. When there arose in cultures across the world, in China, in India, in Greece, in ancient Greece, in Egypt, when there arose philosophies of transformation, what kind of transformation? Of course, desired transformation. Transformation of lead into gold, but thinking in other ways of a sick person into a healthy person. Even the vain hope of immortality. How many Chinese emperors died under the ministrations of their alchemists in the process? What I am talking about is alchemy, of course. When there arose philosophies of transformation, which were sometimes accused of violating the religious systems because they dealt with transformation in which they arose, but which in fact took part of the same myths that powered the religions. And let me just say a word right away. When I say myth, to me myth is a very positive word. We live by mythologies. And so when they took the transformations that I'm referring to, the mythologies by which they were powered are that of Persephone rising from the dead, of the phoenix rising from the ashes, of reincarnation, of the most basic mystery of the resurrection. These are all myths of transformation. And when these arose and needed a logo, a motto for getting into people's minds, because these philosophies were difficult, they chose what already stood for transformation in people's minds, and that is chemistry. This is not your typical view of alchemy. A typical view of alchemy is a pseudoscience, and what chemists think about alchemy is they take what alchemists gave for us in the Middle Ages, they made the strong mineral acids for the first time, and we laugh and we don't look at the philosophy that underlay alchemy because it was abstruse and hermetic, and we laugh a little nervously at something, at the charlatanry that inevitably accompanied the transformation of lead into gold. Here are some typical illustrations, but really this of that charlatanry, you can see what was the fate of most alchemists. If you pretend to make lead into gold, you will be imprisoned because you are an economic resource to your country. And the prince will put you into a nice golden cage to make, and if you can't produce, something else may happen to you. This is a typical alchemical illustration. And you can see here in the background there is a king and a queen being married by some bishop. And in front are some people doing alchemy. Now, when I was in the 1960s, it was given to me to go to some weddings in California of my friends, and I saw some chemistry happening at those weddings, but it wasn't this kind of chemistry. And so what you see here is something on a symbolic plane. This is not a literal, but the idea that you can merge chemistry with a marriage of a king and a queen is very interesting. So that I think what you had here was a philosophy that took chemistry as its motto, and then was, I would say, co-opted by chemistry, transformed, so that the alchemists began to do experimentation, and it merged with regular chemistry. There's a few more things to say about alchemy, many interesting things to say about alchemy. One is that, is not my own, it's due to Mircea Eliade, a historian, philosopher of religion, and what he said was this: modern chemists screaming to high heaven that they have nothing to do with alchemy. They were pseudoscience. We are scientists. Modern chemists have accomplished everything that the alchemists set out to do. For instance, to turn dirt into gold. Well, dirt is the materials from which Merck, Sharp, and Dome begins its synthesis of a successful antibiotic, and gold is what we pay for that antibiotic. And along the way, healing actually gets done. It's true, it's real, so that we have accomplished what the alchemists set out to do. The other thing that one could say about alchemy is really celebration of transformation. And so here we are today, the masters of transformation. We have learned to do more marvelous transformations than the alchemists have done. And what we are missing is the magic of the alchemy, because alchemy had a hold on the imagination of both intellectuals and simple people, for instance, in the European Renaissance. And we, the masters of transformation, are missing it. We don't know yet quite how to put our transformations into the language that you see here. I want to show you this. This is, in part, it's an illustration of a modern, for 1570. You can see the signature here of the Dutch artist Jan van der Straat, who did this for the then Duke of Florence, Cosimo de' Medici. And this was when Cosimo opened his alchemical laboratory, which was part chemical, part alchemical. It's in part a court painting. This man at lower right, who is seemingly making an omelette, is the Duke. In the middle, this wonderful androgynous figure is his then mistress and then later wife, Bianca Capello. And this is in part a court painting, but I want to show this to you because this is the first illustration in world art of the sociology of scientific research. So you see this man over here at lower right wearing spectacles, which were quite a precious item in 1570. You notice he's pointing, he's telling other people what to do. But he is doing nothing. That's the professor. Okay? Now, all the people around who are working are the students. Not much has changed since 1570. Even somebody up there is writing down the laboratory notes. But I just show this for fun. Okay, now let's see. Let's talk about the second way of talking about chemistry. So that was the first one, and we're ending with two interactions of science and society. With time, we learned to look inside the innards of the beast. And what I mean by that is that we learned through the hard work of our hands and minds combined, we understood eventually, and through the help to our fallible senses of our instruments, we understood finally that inside substances undergoing transformations, there were atoms, and much more interesting than atoms, that there were molecules, persistent groupings of atoms. And then we got a microscopic picture of chemistry, that chemistry is the art, craft, and business, but also science of molecules and their transformations. And incidentally, we did not wait for microscopes to show us those atoms and molecules. This was a wonderful episode in the 19th century where we learned something about the inside of matter without seeing it. It was a way of knowing without direct seeing. And that is very interesting for how it happened. But we learned about molecules. Here are some typical molecules. A tetrahedron of carbons with 4 hydrogens, a cube of carbons, a dodecahedron of carbons, and at lower right, a molecule that should be on the flag of Spain, and this year. And this is a molecule that is shaped like a football and is Buckminster fullerene. Now, these molecules are beautifully simple, and the moment I see them, I feel guilty about showing them to you. And why do I feel guilty? The reason is that they are simple, and as such, they have a direct line into our soul. I don't have to tell you that these molecules are beautiful. You feel it immediately. Now, that is telling me something not about molecules, but about you. And this now goes back to a little bit to the talk that Frank Wilczek gave. These molecules are beautifully simple and simply beautiful, and that they have a direct line to the soul. And I know right away that there are other molecules which are not beautifully simple and not simply beautiful, and which I had to work very hard to imagine that they were beautiful or important. And here is a molecule with 9,500 carbon atoms of various kinds, about 5,000 hydrogens, about 2,500 carbon atoms, 700 sulfurs, 700 nitrogens, about equal number of oxygens, 12 sulfurs and 4 iron atoms. And it looks like a mess. It looks complicated. And so people try to simplify it, of course, because that's what our mind wants. Our mind desperately craves simplicity. And so you get pictures like this, where all the hydrogens are removed, and now you see the coils of pieces of it that are helical. Now this molecule, still it looks complicated. It looks like a clump of pasta congealed from primordial soup. It looks like a tapeworm quadrille. This molecule, which is light years away on the lines of simplicity, is the most beautiful molecule I know in the world. It's the molecule of hemoglobin. And where is chemistry? Chemistry is somewhere between the tetrahedron that you saw and hemoglobin, and probably closer to hemoglobin. So the reason I feel guilty is by showing you this, these molecules, I play into the craving of the human mind for simplicity. There is probably a psychobiological reason for that simplest thing. If there were a tiger coming in the back door, please don't look, there is no tiger. But if there were a tiger coming in there, you have 1/10 of a second to run. And it does not pay to start thinking, even to processing what you see in the visual cortex. Is this a tiger or a zebra? And how did a tiger get into the Kursaal? So what's happening is, and Dr. Wilczek implied this, there is too much information and you have to cut away that information. You have to simplify it. Simplification in our mind, however it evolved, is responsible for some bad things. For instance, racial stereotyping is an example of simplification that's used for bad purposes. The particular problem with scientists is they think they are too smart to fall prey to what is in our minds, which is a liking for simplicity. This is why some physicists fall for the idea that an equation must be right because it is simple. And some chemists like these molecules, or if there is a reaction that is to go in, that goes on, and I have made a good living of such reactions, that goes on, and it could go on in 40 steps, and it could go on in 1 step. In the absence of any evidence, we always fall for the simplest reaction, that it goes in 1 step. And sometimes it may, but often it doesn't. So this is a long excursion, but we're really talking about simplicity. Oh, there's one more thing I want to say to the young people in the audience, and I'll put it just as an observation about these molecules. These molecules were made at a certain time and a certain place in the 20th century, all 4 of them. One of them, Buchmünster fullerene, perhaps existed naturally, perhaps exists naturally. It does. It's been observed in some spectra from interstellar space. What I want to tell the young people in the audience is that the molecule which is cheapest today, which is made in greatest amounts today of these 4, is the one that was made latest in the 20th century. I just want you to think about what that means about molecules of the future. So that now let me go back to my tirade against simplicity. If you go, one thing you see about these molecules is you see that they are structures, or perhaps I've drawn them to be structures. There is an architectural sense about them, an architectonic feeling. They are models. here. That's part of what made it. They have a structure. When you go 12 orders of magnitude upscale from these molecules to structures that are made by human beings, you come to the scale of about 100 meters across. That molecule of hemoglobin was about 5 times 10 to the minus 7th centimeters across, about 50 millionths of a half of a millionth of a centimeter across. And now, when you go upscale, you enter human structures. And the interesting thing is that the two poles of simplicity and complexity also enter into human structures. I could have shown you here the Parthenon in Spain, in Greece, or I could have shown you a building in your own country, but I chose a high point of Islamic architecture, the Taj Mahal in Agra, and what you see is the bilateral symmetry, the simplicity which makes this object instantly attractive to the human mind. But now we go to a place that is nearer to you. This is the Transparente in Toledo, and this has nothing in the world to do with simplicity. This is the Baroque, this is the Rococo, and if any line can be made curved, it will be. The aesthetic here is the aesthetic of complexity. It's there also in an Indian temple. Somewhere else in Spain, it's there in the architecture of Antonio Gaudí. Exactly 100 years ago, he built this guardhouse to Park Güell. And no matter how you look at this building, it looks different from every side. This is not simplicity. This is complexity. So I think it's interesting that both for molecules and for more complicated structures, simplicity and complexity fight for our mind, for evaluating what's beauty. Now, I have been, I used to be once in favor of simplicity. I'm now much more in favor of living with complexity. Perhaps it is age that has caused this. But I would like to say that there's something inherently that's interesting about complexity. So let's talk a little bit about that. Or let me tell you a little bit. Let me take an excursion. I'll go up in Park Güell to the benches that were made there. And all of you have seen this place because it is so near to you. And there are some mosaics that you see in these, which were made by Schuschol, I think, of architect friends of Gaudi's. And I want you to think about those mosaics a little bit, because you can imagine, and I can imagine, an entirely different mosaic consisting of squares which are black and white, filling that space. That would be a perfectly good design feature. It maybe would not go with that curve. So what you see here is a curvature that is regular around here, even though it is regular. And then you see these mosaics, and even they are struggling between ideal forms and irregular forms. A circle there, all white, the circles, but then some of the circles are being filled by other broken tiles. Why is he doing this? Why is he not filling this all with black and white squares? What a much simpler solution, and cheaper too, than doing this. Well, I think if you think about this, the reason very simply is this is more interesting. It's more beautiful because it is more interesting. So where does beauty reside in this structure? And Gaudi had a very good connection to beauty. Beauty resides not in simplicity, in regularity. And it does not reside in complete chaos either. Beauty resides at some tense edge where simplicity and complexity are struggling with each other in our mind. You have to have an instinctive reaction. The architect was very good at color matching, that the color matching is okay here, more than okay. But you also, in your mind, we are unconscious, but if you look at this, there is something going on. Why did he fill some circles with other things, while others? That play of something going on in our mind, of comparing it subconsciously with every other structure, the resonances that go on in our mind, that's where beauty resides. In that struggle between simplicity and complexity. And if I have been unfair to simplicity before, it is only because simplicity is much too natural as an aesthetic criterion, and it's much more difficult to make sense of complexity. I want to talk to you about the way people think of chemistry, the third way. And this is already, I have done some of this, because I showed you the Donald Duck cartoons, which give us one way to immediate reaction to chemistry. But let me show you another one. Supposing I was asked to testify to the Congress of the United States and to tell them in a few minutes what was good about chemistry. This will not happen. The reason is that the Congress, the members of the Parliament, our congressmen, don't want to hear what is good about chemistry, or they want to hear mostly about what is bad about chemistry for their particular group of people. Or if there by chance something good has happened, they want to hear about that. But I will testify. I am not stupid. Imagine that hypothetical situation. I am not a politician, but I know that our politicians, you have an unusual situation in Spain where you have one minister who was a very good chemist. But I know that our politicians are, that they really are very interested in mothers and children. And I had better, and in health. So if I'm smart, I should connect my chemistry to children and health. Okay? And so I will do that. I went to a doctor friend and I asked, can you give me some example of what chemistry has done for children and for health? Now this is a difficult slide and I probably wouldn't use it, but what it shows, Dr. Langer told you that the number of cancers in children is small, but it turns out that in developed countries, not in underdeveloped countries where infection is the main cause of death of children, in developed countries, cancer is the second killer of children after accidents. The cancers of children are rather different. They are developmental cancers of the interior rather than of the exterior of our bodies. There is a reason why I did not become a doctor and so disappointed my mother. So I don't know what some of these are. I know that some of them are, but not others. This is a timeline, 1950, 1960, 1975, 1995, nonlinear. And this is the percent of children in the United States surviving 5 years after diagnosis with a certain kind of tumor. And here are different therapeutic techniques. Surgery, always there. Radiotherapy, very interesting. Radiotherapy, despite Madame Curie, did not become an effective technique until after World War II, where sufficient supplies of radioisotopes were available from atomic bomb research in various countries and then became available elsewhere. And here is where chemotherapy begins. And chemotherapy, as you know, is feeding the body a cocktail of chemicals, and some of which kill the tumor more rapidly than they kill normal cells. It is an exercise in kinetics, and it is very difficult for people who have been through it. What you see here is until chemotherapy came online, nothing worked. And at the time that chemotherapy began to work, from around 1970 or so, then what you see is an increase in the survival rate to 75 to 95%. This is about 500,000 children's lives saved. And so any congressman can understand that. So that is my little story about chemistry being good for people. Now, there is always the other side of any story. And out of the back doors of the factories and chemical manufacturers, this is medicine, but I will take the credit for chemistry of this. Out of the back doors comes this. And this is not any specific company. It is just a symbol, an emblem of the infinity of ways that we have found for fouling our own nest. And the situation leads to this twofold image. Remember, what I'm talking about is images of chemistry. The image of chemistry, symbolized here by Janus, the god of doors, built on a typical Roman door. You would see his image. I see doors as very interesting. They're a way in, they're a way out, they're a way of passage, they're a marker for change. And as such, being about change, it is very chemical. Janus here is the two-sided image of chemistry, to heal and to hurt. I can show it to you in another molecule. The molecule its chemical formula is at right, and the substance itself is at left. Anybody here who has had an operation in a hospital knows what morphine is good for. I don't have to tell you. And at the same time, it is addictive. No, not any different molecule. The very same morphine that does good also does harm. And people learn how to deal with this. The very same ozone, well, not the same molecule of ozone, that in the upper atmosphere shields us from the ultraviolet light coming from our life-giving sun, down at sea level in the atmosphere of Mexico City is the main component in photochemical smog, and its role was discovered by Dudley Hirschbach's advisor who did this. It is destructive of both automobile tires and our lungs. Ozone pollution is not a good thing. Anyway, molecules can be both. I think that's interesting. I think that's very human. I think chemistry is the truly anthropic science. When you go to a doctor and you have a child with a fever and he prescribes an antibiotic, you want that antibiotic to heal, and you are also worried about its side effects. Both are there. Now, large galaxies and little quarks are very interesting intellectually. I'm saying this as aggressively as possible. But they will not heal you, nor will they hurt you. But molecules do both. They are on our scale, or on the scale of the molecules in our bodies. In fact, I think that chemistry... Why do I have this here? Yes. This is to remind me that I want to talk to you about the different ways of chemistry, the different tensions that one sees in chemistry. And here is another one. I've just talked about one, harm and benefit, both embedded in the same molecules. Now I want to talk about another one, natural, unnatural. Now here is a class of molecules which I would be sad to see the world without. These are the plants of the allium family, which include onion and garlic, and on which the cuisine, which make life interesting. I don't have to tell you. But the question that I wanted to remind you of is to ask, is garlic or are garlic and onions natural? Or are they man or human made? Well, the question is not as simple as you think. A few plants of garlic in the wild are most certainly natural, but a field of garlic is not natural. It is agriculture. And civilization came with agriculture, and agriculture is a very interesting confounding of the natural and the unnatural. It is human beings using the natural for their own purposes. And that is part. I wanted to tell you a little bit also about, to remind me as I move through this, I wanted to tell you a little bit about another tension that is a little bit related to the unnatural, natural, and this is about creation and discovery. So one of the things that makes chemistry different as a science is that people do this, which you see here. Now, you may like it or not like it. It comes in different settings of a person, hand and mind, struggling with the molecules there in a laboratory, or it comes in a large chemical factory. But what people are doing here is they are synthesizing molecules. Molecules largely which were not on Earth before. Not like hemoglobin, but different from it. And that aspect of creation puts chemistry very close to the arts. Because we are making things and we are studying, transforming things and studying the effects of that transformation. Lest we get too high on this in the sense that we think of art as being something high, not that we pay artists that much, and of technology being something lower, it also puts chemistry very close to engineering, because engineers are also make things, and they had better work. And when the airport at Bilbao, where we arrived on Sunday, when part of it didn't work, something had to be done to make it work. So there are transformations but the transformations are very, very human. I just want to show you it's there everywhere, but in particular I'm talking about medicines. If you are in a hospital, not at home, an antibiotic of choice is Primaxine, made by Merck, Sharp, and Dome, those people who have learned how to transform dirt into gold. It's a complex of two antibiotic components, imipenem and cilastatin. And here is how one of these components is made. It starts with something simple in nature. It's transformed by a sequence of transformations. You can see the molecule growing before your eyes before it comes into something close to penicillin, which is this imipenem over here. The other molecule is totally synthetic. This molecule is natural. It's absolutely astounding how any action of human beings confounds the natural-unnatural division that our simple mind would like to have. Here's an antibiotic that was found first, which was found natural in a beautiful species of a violet mold growing, which gave this antibiotic. But the mold didn't give enough antibiotic to produce it, so it's made synthetically. But where is it made synthetically from? From something natural to begin with. Of course, what else could it be made from than from something natural along the way? And then it wasn't good enough, so a completely synthetic molecule was added to damage the enzyme in the bacterium that has learned how to take this molecule apart. It's an incredible story, but it's a mixture of natural and unnatural. I come to the tensions that I see in chemistry and which are behind behind the title of this talk, the Chemistry's Essential Tensions. And I told you about some of these, of large things and microscopic views, of simple complex, of symmetric and asymmetric. I've talked very little about harm and benefit, but that one is on everyone's mind anyway, and I don't have to say anything about it. Natural, unnatural, creation, discovery, very interesting kind of science where creation figures importantly. Synthesis, analysis. I could talk of more of these things, but I want to actually finish with a story again for the young people in the audience, because I was unable to tell it on the other day. You saw me use, in this talk throughout, you saw me use artistic examples, largely of the visual arts, to illustrate some of the ideas. I unfortunately did not use music, though I could have done that in a number of these things. But I want to tell you a little bit, not by way of explaining why I used artistic examples, but I want to address this difference between art and science, which are similar and different. I want to address it through a story here of masterpieces. So here is a masterpiece of chemistry. This is not a good chemistry lecture room, but if this were a chemistry lecture room, up there would be the periodic table of the elements. Now what I want to address is the feeling that I perceive from many students to have when they are confronted with masterpieces, like this periodic table of Mendeleev's. When they are confronted with masterpieces, and one of the feelings about human beings is we feel that we cannot be as good as others. So one of the feelings is simply, how can I ever make such a thing, such an advance in chemistry as personified by the periodic table? So the way to answer that question is not to look at the masterpiece, but to look at the way that the person made the masterpiece. And that means to look at what happens, what happened in the making of it. Now, one thought you might have is perhaps the best person to ask would be the person who did it, Mendeleev. But he's no longer alive, but that's not the point. Historians of science have taught us that often the way people who did the thing describe later how they did it, that it often, let us not say that it is incorrect, that it's a good story. Okay, because what happens is what Mendeleev did was good. It was praised as good. He was invited to many congresses, like this one. He gave many talks about it. People asked him after dinner, how did you do it? And he said, he gave a story. The story he gave was that he had playing cards. He was beginning to write a textbook about chemistry. He did this when it was first possible to do this, 6-7 years after the atomic weights of the elements became available. And he ordered, I don't know where he got the playing cards from and how he wrote on them, but he wrote on the cards the symbol of the element, which was already set there, like Br for bromine, and the atomic weight of it. And then he arranged the cards so that elements which behaved similarly chemically were ordered in some way while keeping an ordering of the atomic weights. And he got sort of a snake out of this. That's what the story he told. And every time he told it, it got better. And if you look in his files, there is no playing cards. What there is here, it is the first draft of the periodic table. And you see here the elements here the symbols as they are today, because from 1830 on, those symbols were accepted. If you see here fluorine, oxygen, nitrogen, carbon, boron, all you have to do is to turn this table by 90 degrees clockwise, and you will see it as our table. What has he done? He's ordered the elements at the bottom, and as he fits them into the periodic table, he crosses them out. This is like a shopping list. Okay? And then here he's writing in a mixture of German and, he says, in Russian, because he was educated in Germany. There are 3 elements left over which could not fit into the periodic table the first time he did it. It is in the nature of theoreticians to make things fit in that don't fit in. And he made them fit in. What is the most beautiful thing about this? The most beautiful thing about this is the crossing out, of course. It is the prima facie evidence that this was done by a human being and not a machine. A human being trying to struggle to understand this. And where will such drafts be in the age of the computer? That's something that worries science historians a lot. Okay, so here we see a human being struggling with the facts, and it's there. And I think it's beautiful, and I think it should encourage you. But there's something funny about human beings. If you show them something like this, which shows that it takes work to be a scientist, that perspiration counts. We are such romantic human beings. We think that surely there must be some aspect of human creativity where perspiration is not what counts, but inspiration is what counts. And the usual focus of such romantic dreams is our poets. So here is a typical stereotype of a poet. He's walking around all day on along the sea here and does nothing. And then at some point the poet whips out, after walking around for a long days, whips out a notebook. I know I had it someplace. It's here. And writes down the poem. It comes like Athena out of Zeus's brow, in one fell swoop, beautiful and complete. Well, let me show you how it goes, really. Here is a well-known poem in the English language. Tiger, tiger, burning bright in the forests of the night, what a mortal hand or eye dare frame thy fearful symmetry. Here is the last draft that we have of this poem. In Oxford's library, he has a phrase, dread grasp, which he first puts in here, but then it doesn't fit in here. And he knows it's a good phrase, it's poetic. He's going to make it fit in someplace. So he tries it here, and it doesn't fit in here, and eventually it finds it in here. I know the feeling exactly, because I do both of these things. This is salvage. You have something interesting, a phrase, and you use it. You're going to use it someplace. That phrase is strong. It has power over you. And so I now have put these two side by side, and I come now to the end of the last slide of my talk. Science and art are not the same. There are similarities, which we could talk about, and there are differences. But there is something that comes out from looking at these two drafts, one of a great poem, one of a great achievement of science. And one of the feelings I'd like for the young people in the audience is that now that I've shown you that it can be done by human beings with some sweat and work, I think it is within your reach as well. Thank you very much.